Hello, Longhorns. We're moving on to lesson 14, looking at properties of waves. You'll be excited to know there are no equations in this particular lesson. This is one of those times where we're going to have a lot of conceptual questions, and we want to make sure you can visualize this wave in your mind. We'll talk about different types of waves, and we'll also review parts of the waves, and to make sure you have it. We're coming from pages 380 through 386 in the textbook. It's a great idea to also go back through the textbook and think about some of the things you've seen in your PowerPoint. I would love for you to either print out the PowerPoint and make notes, or create a little journal that allows you to go through and take notes as you find new information. So let's get to it. We have a lot of waves, and the biggest thing is most waves are going to move through matter, and this matter is called a medium. Now, when it comes to examples of a medium can be water, or it can be air. It can be plasma. It can be anything that it's moving through. And if that wave has to have a medium, it's actually going to fall into a different type of category. We have two types of waves: longitudinal waves, and we have transverse waves. If you think about it, imagine we have a slinky, and we are compressing and depressing, or pulling apart the same slinky. You'll notice that back and forth motion makes a longitudinal wave. So they get really compressed and then expand. They go back and forth. Long is longitudinal. The waves that we see that are more graph-like, that give me this nice little axis in between, these are known as transverse waves. The waves that have the motion that goes up and down. If you think about a football game and they throw the sign up that says do the wave and everybody stands and moves, those are transverse waves. If it is a wave that is being compressed and expanded, it's going to be a longitudinal wave instead. They've also labeled amplitude. Amplitude, remember, goes from the highest point of your wave down to the origin. So think about your graph, and this will show you exactly where your amplitude is located. Now, we have mechanical waves, and these require a medium. And remember, a medium can be air, water, anything that wave is going to move through. And most of your waves, seismic waves, which are like your earthquake waves moving back and forth, and sound waves fall into this category. You're going to hear me ask you the question: if you are an astronaut in space, and if you scream, can anyone hear you? I want you to look that one up and let me know what answer you come up to. And of course, have an explanation to support your answer. Now, transverse waves, if you take a look at the motion, this will be moving up and down, up and down. So we have my up and down motion, and I have my energy that's going to be transferred forward. There are different vibration types, and whenever we talk about vibration, remember this is going to be your longitudinal wave. So they're going to be more on a parallel axis to one another. Examples of your longitudinal waves can be sound waves as well. It just depends on how they're moving and where they're moving. All right? You'll notice the change in my arrow. Transverse was going up and down, north and south. Longitudinal waves will go east and west, left to right, back and forth. Now, surface waves. Whenever you're talking about ocean waves and you want to be really specific in what type of wave it is, a surface wave or an ocean wave has a circular motion. So you'll notice that there's a really big surge, there's a rise, and then it caps. Your white caps come out and it's going to curve back around. So this makes a nice little circular motion. These waves are both transverse and longitudinal. We'll also learn that there are different types of motions when we're dealing with an earthquake. You can go back and forth, but the most damaging waves are those that shear and go up and down. So we will have some instances in nature that are a combination of both. Now, mechanical waves, remember, mechanical starts with M. Mechanical waves need a medium. So they have to have something to travel through. These can be transverse, longitudinal, or surface. What they all have in common is that your mechanical waves need a medium. But there's another type of wave, electromagnetic. And if you look at the name, electro reminds you of what? Electrons or even electricity. Magnetic, when we take those little refrigerator magnets and try to put them together, and they're always struggling to go apart. Electromagnetic waves is a proper name for light. Light is a little bit different. Electromagnetic waves are only transverse, and the other difference is they do not require a medium. Now, parts of your wave. The highest part of my wave is going to be the crest. The lowest part of the wave will be your trough. We've talked about amplitude before. So we're going from our mid area to the very top, my crest. That will measure our amplitude. If we're looking at wavelength, we're going from two identical parts. So if I go from crest to crest, that's a wavelength. Or if I go to the bottom of my wave, from trough to trough, that's going to be a wavelength as well. And we're going to realize and learn another Greek letter because wavelength is represented by lambda. And we'll look at that symbol as well. Now, just to lay it out, amplitude, you have your crest of the wave here, a very top portion in purple. Your amplitude is going to go from the origin or the midline all the way up to your crest. We have our trough in green at the very bottom. And if I pick two identical parts of a wave from crest to crest, it will be equal to one wavelength. And there are problems that will ask you, how many wavelengths travel through this point? This is another way that our Corps of Engineers will determine how large should a levee be? How strong must this bridge be? Because waves move energy, and that's a constant impact every day, all day. This diagram we've seen before, and the only other term we needed to remind you of is period. Period was represented by the capital T. So the number of wavelengths that go through a particular point in a certain amount of time. Period is measured in seconds. We've taken a look at frequency in our last video. So how many wavelengths are able to go through a particular point will be frequency. And remember, frequency was represented by a lowercase f. Period was represented by a capital T. It's tied to time. Now, you can either speed a wave up or slow a wave down. And if you think about your sound, the music that you listen to, if I take the normal sound of a voice and if I slow it down, it's going to lower the voice. The opposite happens as well. If I take that same voice and I increase my frequency, it goes up like a chipmunk. So think about the sounds you hear and think about those things you interact with, and it'll help you keep your vocabulary nice and tight. Before you go, if you have any questions, of course, email those to me. If you would like to see another look at this material or an alternative view, I've included a link to a YouTube video for you as well. The goal is for you to come every day to class with questions, things you hear, things you see, things you read on this topic, and we can definitely address those. I'll see you guys in class.